Hi and welcome. It's Saturday Extra and it's Physical Sciences. My name is Tinigo Kosa and I welcome you once more. Today we're going to have a lesson based on photoelectric effect. Now, photoelectric effect. Before we go any further, I just want you to draw your attention to something very important here that will help you focus in this lesson. One, the topic here says photoelectric effect. The word photo, what does it mean and where does it come from? You would be familiar with words like photosynthesis and photograph, okay, such kind of words. Now, this word photo is associated with light, right? So we're talking light. The word electric obviously has something to do with charge, because we can have electricity from charge. And specifically in this lesson, this word electric will have some reference to electrons. Okay, so we'll be talking a lot about light and electrons and the effect of that. Okay, so and as we move on in unpacking this lesson, we need to know something about the dual nature of light. Okay, now this is something to say that light can be explained in two ways. Okay, we can explain light scientifically in two ways. And what are those two ways? It's that light has got a wave nature and that light has got a particle nature. We'll unpack these things as we move on in this lesson, and it will be quite interesting. The second bullet here talks about the particle nature, as I've already indicated there. So this one, in particle nature, it is related to light having things called photons. Now, this is something I'm going to explain further as we move on in this lesson. So the particle nature of light, in other words, that part of light, is best explained when we look at photoelectric effect. These helps us to understand the particle nature of light. And I will, in the lesson, of course, refer to things like when or what kind of scientific phenomenon tells us about the wave nature of light. Now, when we talk of the particle nature of light, we can't do so without talking about the energy equation, which is E energy equals HF. Now, I will explain more what H is, but I think by this, at this point in time, having done a lot on electromagnetic radiation, you would understand where F comes from. F is the frequency. All right. And we did refer to this equation here when we were talking electromagnetic radiation, because we were saying that those waves are actually carrying some energy, and that is how we can find the amount of energy carried by those vibrating particles. Right. Another thing that we'll be talking about in this lesson, it's something called work function. And this has to do with metals, metal surfaces. We will explain more, of course, on that. And the last part here, we'll be talking about what happens to electrons that are ejected and the kinetic energy that they will be having. Right, so that is the introduction of our lesson. Now let's quickly have a look at the dual nature of light. The dual nature of light, like I said, this tells us that we can explain light in two ways. So we have got two ways to explain light. These two ways, like I've said, it's that we can say that light has a wave nature, or it can be explained using the wave phenomenon. That light actually is something that exists in the form of vibrations, okay, regular repetitive motion, that's a vibration. And for us to understand, or the sort of evidence that we have that tells us that light has some wave nature, it's when we try and look at the characteristics of light, and we find that light actually does undergo diffraction. Now, where does diffraction occur? Diffraction occurs in waves. That is the bending of waves around obstacles. Now, in a simple way, that's how we define it. In a simple way, we'll say that diffraction is the bending of waves. Bending of waves around obstacles. Okay, now that's a very simple way of defining it. I'm just trying to explain here to say, when we look at waves, waves undergo diffraction. Now, light does undergo diffraction as well. And because light can undergo diffraction, we say we can use diffraction to explain that light has got a wave nature. Light has got a wave nature. But then, the other part of it, because we're saying light has got a dual nature, the other part, which is the second part, is that light is also viewed to be having a particle nature. Now, particles, you would know, particles, maybe this would represent particles. So light is also looked at or viewed as something that is formed of particles. All right? Now, particles, when they are in motion, we know that those particles will be carrying energy when they are in motion, and when they hit other objects, they are going to release that energy, and that energy can be converted into other forms, because we don't have any situation where energy can be destroyed. It can only be transferred from one form to another. So particles of light. So light can also be seen as having a particle nature. And the scientific phenomenon that helps us to understand light as having particle nature, it's the topic for today's lesson, which is called the photoelectric effect. And we're going to unpack this clearly as we move on in this lesson. Right. Now, what is this photoelectric effect? Photoelectric effect, it's something that it's seen or it can be observed happening when light of particular frequency is shown on a metal surface. It will cause electrons to be ejected from that metal surface. Now, this will happen only if the light that is shown on that metal surface is bringing in energy packets. We'll explain further about these energy packets as we move on into the lesson. That are having these energy packets having enough energy to cause the electrons to be ejected. So the ejected electrons, once they are ejected, they can move, all right? But then they can only move provided that they contain enough energy after that. In other words, if you have electrons on a metal surface, say this is a metal surface, and the dots represent electrons. these electrons, when light is shone on them, okay, so you shine light on this metal surface, these electrons can be ejected. So this electron, for example, can move out. All right? Now, when it gets ejected, it can move out only if it has got an excess of energy that it can use to carry it forward or to make it to move. Now, if that energy is not enough, this electron, if it is this electron, for example, it can be ejected, it goes up, but then because maybe it is not having enough energy, it can remain or go back to where it was found or where it was before the ejection. So that is what the definition is all about. Photoelectric effect is a phenomenon where light of specific frequencies will cause electrons from a metal surface to be ejected. And if those electrons are having enough energy, that can result in electrons moving. In other words, gaining kinetic energy or having some speed to move off that surface or move away from that particular surface of the metal. Right. Now, let's begin to unpack this photoelectric effect. In the first place, for us to understand light as having a particle nature, we need to understand that therefore there will be small packets of energy carried by a specific light or a light of specific frequency. Now, those specific packets of energy are called photons. All right? Now, these photons are carrying specific electromagnetic radiation, and that is called the quantum of energy. In other words, it is carrying, these photons are carrying discrete amount of energy. That amount of energy that is carried by a particular photon can only be that energy. Why can it be just that energy? Because you will remember earlier on when we looked at the energy equation, HF. This energy depends on the frequency, F. And the frequency of a particular light, it's specific. It belongs to that particular type of light. And therefore, if we're looking for the energy carried by a photon of a specific color of light, that will be the energy. It cannot be more, it cannot be less. So we say that that energy is quantized. And therefore, we use terminology such as a quantum of energy. Now, quantum of energy means that that particular type of energy, it's specific, it is discrete, it belongs to that particular color of light, which is, of course, determined by its frequency. A photon contains specific amount of energy, as I've explained, and we say that this energy of a photon is quantized. It is exactly what it is. It cannot be more, it cannot be less. Maybe just to give or to relate this to something in real life. If we talk of a dozen of eggs, we know the number we're talking about. We're talking about 12 eggs. So when somebody speaks to you and say, go buy me a dozen of eggs, it means that that person knows exactly the number of eggs you are going to bring back. If you buy the 12, which is the dozen, and add 3, and then you've got 15, that is not a dozen. So when we talk a dozen, we're talking about specific number of eggs, specific number of things, of items. In the same way, when we talk energy being quantized, the energy of a photon being quantized, we are saying it is that specific energy. It cannot be more, it cannot be less. And it is, of course, given by the energy equation, E equals HF. Right. So This energy of a photon, like I have explained, is directly proportional to the frequency. And that is given according to Planck's equation, which is the energy equation E equals hf. Right. So that is the energy equation. And h, I said to you, I'm going to explain what h is. H is a constant. It is called Planck's constant. Okay? So this is Planck's constant. Planck's constant, and its value is that. Okay, it is always 6.63 by 10 to the power minus 34 joules second. That is h. So if h is a constant, it means that the amount of energy, this energy, it is totally dependent on the frequency. Now, this frequency could be a frequency of red light. So a photon of red light will have or contain or possess that specific amount of energy, which is, of course, quantized. It is the frequency of red light, and therefore the photon of a red light should carry that amount of energy. It cannot be more, it cannot be less. Right. Let's move on now. We are going to move on to do some example now. We will have example 1 and see how we can use the energy equation to solve some problems. Now, how much energy does electromagnetic radiation of the following frequencies have? So we have got A, B, and C. In A, we've got infrared. In B, we've got orange light. In C, we've got ultraviolet. Now, let's see how we can answer this question. We know that the energy equation, so let's look at solutions here for A. Energy equation is given by HF. So a photon of infrared light will have this energy that will be found by the Planck's constant. And remember Planck's constant? 6.63 by 10 to the power minus 34 times, what is F? The frequency of infrared, which is 3.0 by 10 to the power 14. Right? And what will the answer be? Right? Well, at this point in time, we make use of a calculator. We need a calculator to do this quickly. So we have 6.63 times 10 to the power minus 34 times 3 by 10 to the power 14. Okay, so, and let's see what that gives us. It gives us 1 point, let's have that answer, 1.989 by 10 to the power minus 19. So it's 1.99 by 10 to the power minus 19. You're calculating for energy, and the unit is the joule. So that's what we have. So that's how we calculate for it. And this energy, like I said, if you're talking infrared light will be bringing a number of photons of infrared. Each photon of that light will be carrying this amount of energy. So that will be the energy carried by a photon of infrared. Let's look at the amount of energy that would be carried by a photon of orange light. Again, we know that the energy equation is E equals HF. Now, I need to pause here and bring in this exam idea again. Remember, when you are working with formulae in physical sciences, always make sure that you write down that definition of the formula. In other words, write down the formula in full first before you start substituting into it. It would be quite easier for me here to just start, okay, H is that, F is that, and just say E equals 6.63 by 10 to minus 34 times 5.0 by 10 to the power 14. But I need to follow the principle all the time. I must write down this formula first before I substitute into it. The substitution comes next. Then I ask myself, what is H? H is the Planck's constant, which is 6.63 by 10 to the power minus 34, right? This is multiplied by the frequency F, and what is F? For orange light, F is 5.0 by 10 to the power 14, all right? And then we can find this quickly making use of a calculator. Now this is 6.63 by 10 to the power minus 34 times 5.0, which is as good as 5 by 10 to the power 14. And what is the answer? The answer is 3.315, so I'm going to make it 3.32 by 10 to the power minus 19. I think you know why I'm making it 3.32 by 10 to the power minus 19 joules. Okay? Now, I have rounded off that answer there. Remember rounding off as well. That's important. Now, let's come to number C. Number C, we're looking at the ultraviolet light. Ultraviolet light, UV, and this is, of course, the harmful part of white light. Okay? When it reaches the earth, it actually makes some people to even have skin cancer because of its penetrative ability. It penetrates into our skin, into everything, and it is harmful, ultraviolet light. But, of course, it is also used for something beneficial. You would see when you go to butcheries, okay, you will see this nice-looking bluish light. It is ultraviolet, and it is used to kill bacteria. So there is also some good use of ultraviolet light, but we don't want it on our skin, definitely. Good. Now, coming to number C, ultraviolet light. Again, I'm looking for the energy carried by a photon of ultraviolet light. So I'm going to write down my equation, my definitive equation here, the equation that gives me the amount of energy that I need that is carried by a photon of ultraviolet light. This will be given, of course, we know the Planck's constant, 6.63 by 10 to the power minus 34 times. What is the frequency of ultraviolet? It's given to us as 6.0 by 10 to the power 14, right? What is the answer? We need our calculator quickly. Let's work it out. We have here Planck's constant 6.63 by 10 to the power minus 34 times 6 by 10 to the power 14. What is the answer? The answer is given to us as 3.978. Writing this into two decimal places, it's going to be 3.98 by 10 to the power minus 19. So it's 3.98 by 10 to the power minus 19. This is joules. That's the unit for energy. So I'm calculating for energy. E is measured in joules. Now, that's how we calculate for the energy carried by a photon of light. If it is an infrared light, the photon of light of that infrared will carry that specific amount of energy. In this case, it will be 1.99 by 10 to the power 19. So that is exactly the energy that will be carried by an infrared light. It cannot be more, it cannot be less, because we're saying that this energy is quantized. In the same way, it could be a green light, okay? Photon of green light. It will also carry a specific amount of energy. That energy is quantized. It cannot be more, it cannot be less. It has to be exactly what it is, because it depends on the frequency of light. So that's how we understand or explain the quantization of energy, and the fact that that energy cannot be anything different. Okay, now let's move on and let's have a look at what happens then. Now, I want you to understand this very carefully. What happens then when the energy coming into a metal surface, for example, that packet of energy, that photon, does not cause electrons to be ejected? Why? Why would sometimes that packet of energy in a particular metal cause electrons to be ejected, but not necessarily cause the electrons to fly off and move away? Why would sometimes this packet of energy coming in, called a photon, would hit a metal surface and electrons are ejected and they move? In other words, they gain energy to even move off that surface. Why are these things happening? We are going to try and answer those questions now. Okay, firstly, let's look at something called threshold frequency, and we call it F0. Now, what is threshold frequency? Threshold frequency is the minimum frequency of light needed to eject an electron from a metal surface. Now, remember that the energy that is carried by a photon depends on the frequency. Now, if for some reason a particular metal, say zinc, would have a threshold frequency of 2 by 10 to the power 17 hertz. That means that if you bring in light with exactly that frequency, it is going to be able to eject electrons. So that is what we call the threshold frequency, because it is going to cause the electrons to be dislodged from their positions. But this threshold frequency is not big enough to get the electron to move away, but it is just good enough to dislodge it, to dislocate it, to eject it from that metal surface. That's all it can do, and that's the threshold frequency. Now, this threshold frequency is related to something called the work function of a metal. You would see this work function has got a 0. We call it W0, work function. It is, of course, related to the threshold frequency. Now, work, if you go back to mechanics, we know that work, it's when you expand energy, you make use of energy. Work is energy expended. So, in other words, work is defined in terms of energy. So, this work function here, we can also say that this work function is the minimum energy package that is needed to eject an electron, from a metal surface. Okay, so now, if this work function is just that minimum energy, remember the energy equation, E equals HF. If we make use of the threshold frequency here on this equation, such that we have the energy, just the minimum energy needed to eject an electron, then this energy is actually giving us the work function of that particular metal. Okay? Now, let's explain further this issue of of work function for a metal. The work function, you would say, it's a property of a metal. The work function of zinc, for example, won't be the same as the work function of copper. It won't be the same as the work function of aluminium. It won't be the same as the work function of, say, magnesium. They are all metals, but they have different work functions. Why? Because work function is a property of that metal. The work function is saying, for any light to eject electrons from me as the metal, it has to bring this specific amount of energy. In other words, in terms of your frequency, that frequency should be good enough to be able to get the electrons of this metal, if it's zinc, to be dislodged. And you would find that if you bring the work function that's equal to the energy equal to the work function of zinc, electrons will be dislodged or dislocated in zinc. But you take the same light, bringing in the same energy or bringing in the same photons of energy, but then different metals, say copper, and you find that no electrons are being ejected. Why? Because the threshold frequency or the work function of copper is not the same as that of zinc. Right. Now let's proceed on this one. So the minimum energy needed to eject an electron from a metal surface is called the work function. So the work function, like I have said, work is defined in terms of energy. So energy equals to HF. If we make use of the threshold frequency on that equation, the F0, then we are calculating for the work function for that particular metal. Right. Now let's come to the second part of this statement. It says here, if the energy absorbed by an electron is greater than that of the work function. In other words, if E, which is HF, is greater than WO, what happens? Than the work function. If E is greater than the work function, what happens? The remaining energy is used to set the electron on motion. Now, I need to explain this further. If energy that is brought in by the photons of light, so this is the energy of the photon, which is given by HF. If it is greater than the work function, so you have a situation where you have got a metal surface. Say this is a metal surface with electrons moving all over the show, because electrons are free to move, and then protons are stationary in there, so they are moving all around these protons, which form the nucleus of the atoms around here. The electrons are moving around. If these electrons, let me just use a different color for electrons. Let me use a black one. There is an electron, 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 electron. There could be more, and of course, many of them are there on that surface. But just allow me to have those ones there, just to try and illustrate what's happening here. The energy that comes with a photon. Say, let's start it from this one here. Say you just have enough energy, which is given by H times the threshold frequency, which is exactly the work function of that metal here. When that photon of energy comes in, say it's this one here. It comes in, it hits the surface there, okay? And it hits this electron. So that's a photon of energy. When that electron is hit, it will be dislodged. In other words, it will vibrate, can move that way and this way, or up and down, but comes back to its position. Why? Because this energy is just enough. This is just enough. Just enough to eject an electron. Just enough to eject an electron. That's that energy. So this is your energy equals to your work function. E equals to EW there. But then you can have a situation where another packet of energy comes here, and let me use a longer ray here of light there, saying that this one, the E that is coming in here is greater than the work function. So HF is greater than WO. What is going to happen to that electron? When this energy hits an electron there, that electron is going to be ejected. And not only ejected, but then it will move off the surface of the metal. Why? Because it has gained enough energy to can do that. We can explain that further. Now, let's have a look at it. When the energy of the photon is greater than the work function, we have a situation where this energy that is coming in works. We know that this is given by HF. What it does, it provides that enough energy to dislocate, to dislodge, to eject an electron. But then, because this energy is more than the work function, the energy used to overcome the work function, if you like, if we want to get the total energy that was brought in by the photon, it will be that energy that has been used to overcome the work function plus the energy that caused the electron to move away. Now, what type of energy causes things to move away? In other words, what type of energy is associated with motion? The energy of motion, we call it the kinetic energy. So, when part of this energy is used to overcome the work function, to dislodge an electron, the remaining energy is used to get the electron in motion, to set it in motion. And that energy is the energy of motion, EK. Right. So we have a situation where, in this case, let me just say this to consolidate what I've just said. You have got a situation where you need, let me put it in some real life and go back to the example of eggs again. You've got a situation where somebody only needs 8 eggs, but these eggs can only come in dozens. So you go out there, you can't buy exactly 8 eggs. You can buy a dozen, which is 12. You can buy twice the dozen, which will be 24. You can buy 36. It is bought in 12s. That's what I'm trying to say. So when you buy something in 12s, which is a dozen, and somebody only needs 8, then you go to the shop, buy the 12. You come back home, you give the person exactly what he or she needs. It's 8. That is your work function. So you take the 8, you give it to that person. But there's an extra. There's a 4. And that 4, you can use it for your own benefit. Your own benefit could be that you can sell them again in singles if you want to, or whatever you can do, or fry them and have them for breakfast or whatsoever. But the thing is that you had 4 extra, and that extra you use it to your benefit. In the same way here, the energy is quantized. It comes in packages, right? So this photon of light brings this amount of energy. But this amount of energy is more than what is required to dislocate an electron. So what it's going to do when it hits the surface of that metal, it's going to dislocate the electron, and after dislocating it, there will be remaining energy that didn't have anything to do in terms of ejecting that electron. So that remaining amount of energy is going to be used as kinetic energy to get the electron in motion, set it up in motion, and it is moving or moving away from that particular surface. And of course, scientifically, we don't want to lose anything. We can have some means of capturing this electron and make it do some work in some way. So that is basically what this equation here is talking to us about. The energy coming in, the energy of that photon coming into the metal surface is bigger than the work function. So part of this energy is used to overcome the work function, to give the person his or her 8 eggs. Then you are left with the 4 eggs, which is the remaining amount of energy. Use it to your benefit and have your electrons set up in motion. So the remaining energy is used to set the electron on motion. Right, let's move on now and unpack a few more things about this issue of energy carried by a photon versus the work function. There are actually 3 conditions I'm going to talk to you about based on this. Very interesting situations, and I believe you're going to enjoy this and understand it better. Let's look at it. We have energy of a photon versus the work function. The first condition here, we have a condition where you could be having light carrying photons, where each of those photons is carrying energy. And of course, that energy is defined by that equation, but that energy happens to be less than the work function. What is going to happen? I think at this point in time, you should be able to answer me on that one. What is going to happen when the energy carried by a photon of light is less than the work function? What will happen on the metal surface? What will happen with the electrons? I can hear some of you mumbling the answer there, and some of you are correct, of course, to say that what is going to happen is that we will have electrons not ejected. There will be no ejection of electrons here. There will be no ejection of electrons. So no ejection of electrons in this situation. Why? Because the energy coming in onto that metal surface is not good enough. If we need 12 eggs, somebody is bringing us 7. So that is not good enough to make us happy, okay? So that energy is not good enough to cause any ejection of electrons. Let's look at the second condition. The second condition is the condition where you have got the energy carried by a photon of light is given by h times the threshold frequency, F0. Remember that one? In this situation, what is going to happen? The energy carried by this photon is just enough. It's exactly what is required to eject an electron. So here, there will be electrons ejected, okay? Ejection of electrons. But something is not going to happen. What is that something? An electron will be ejected, okay? But that electron won't have enough energy to fly off the surface of the metal, to move away from the metal of the surface. In other words, it will be ejected, dislocated, dislodged, but it won't be removed from that metal surface. So the electron stays there, it is ejected, but no motion, no EK, okay? No kinetic energy. There isn't enough energy, there isn't enough excess energy apart from the work function to give the electron enough energy to be moved off the surface of the metal. So electrons will be ejected here, but no motion, no EK. Let's look at the last condition. And I love this last condition here because, you know, life is such that, or nature is such that there's nothing perfect. You know, you can't say, for me to dislocate this electron, I need 10 joules of energy, so I'm going to put together light that will bring exactly 10 joules of energy. It will always be less or more than what is required. That is what the reality will always be. In other words, the middle condition here, it's a very rare condition. You don't find it easily in real life. What you find easily in real life is condition 1 and condition 3, where you either have less of what is required or you have more than enough of what is required. Okay, now let's look at it. Condition 3, energy that is brought in by the photon this time, E equals HF, is greater than WO. You can see that they are not using F0 here for threshold, but they are using plain F. This energy is greater than the work function. And again here, you should be able to give me an answer as to what will happen if I bring light carrying photons of energy that has energy greater than the work function. What is going to happen to the electrons? You should be able to give me that answer. Some of you are saying it correctly, of course, to say electrons will be ejected in this situation. Electrons will be ejected, just like in the rare condition here, condition 2. But what is different now is that when these electrons are ejected, when you are bringing energy greater than the work function, part of the remaining energy is used to set the electron in motion. So electrons will be ejected and set on motion or made to move. Okay? Now, these are the 3 very important conditions that you should know, that you should understand. Okay? Now remember, when the energy coming in a photon of light is greater than the work function, you've got electrons ejected and moving away from the surface as well, gaining enough kinetic energy to move off the surface. How do we then account for all the energy that has been brought in by the photon? Because energy cannot be created nor destroyed. It can only be transformed from one form to another. It would mean that we have a situation where E comes in, and that E, which is HF, is used to overcome work function, and part of the remaining energy, the E, because it's greater than WO, part of that energy becomes kinetic energy. Okay, that equation there, very important. Let me now give you a quick summary of what we've been talking about with regard to the 3 conditions. 1, we have got this condition here, where we are saying that the energy carried by the the photon of light is less than the work function. And we said here, no ejection of electrons at all. This situation here happens when you have got light of low frequencies. Okay, lights such as red, orange, okay, in that region there. Not in the region of ultraviolet, which will be in the far right in terms of increasing frequency. Right. So when you have got these low frequencies of light, the electromagnetic radiation there is not enough to cause electrons to be ejected. So they don't cause electrons to be ejected. Now, something very important in this summary. When you have this energy of a photon, okay, less than the work function, you are not going to cause electrons to be ejected. Now, think of it in this way. You've got light that, say, red light. You are shining it on a metal surface, say zinc. And the work function for zinc is much bigger compared to the energy brought by the photon of red light. Okay? So you bring in that light. That light is made up of millions of photons of red light. Okay? And what happens that you should understand is that for every photon, one electron can be ejected if it is bringing enough energy. So each photon works on an electron. You can't have one photon ejecting more than one electron. So you've got one photon, it's one photon working on one electron to one electron. That is the rule, okay? But then in this situation here, we know that no electrons are going to be ejected. So if you've got that metal surface there, and you've got electrons on that surface, okay? You've got electrons on that surface. You shine some light there, okay, hitting the electrons. This light here is of low frequency. It does not carry enough energy, so this electron won't be ejected. So even if you bring in, remember that I said there is millions of photons of that light coming onto the surface. Each one of them is carrying energy less than the work function. In other words, E for each of them is less than WO. For each one of them, it's less than WO. Even there, even there. That's what we are having. Electrons here won't be ejected. They will stay on the metal surface. So even if I can increase the intensity, even if I can increase the intensity of this electromagnetic radiation, which is light, even if I can increase the intensity, this increase in the intensity won't cause any electrons to be ejected. Why? Because increase in intensity just means that you have got more of the photons coming in. But all these photons are carrying energy less than the work function, and therefore they are not going to cause any electron to be ejected. Very interesting. You make your red light brighter, no electrons will be ejected. You make it dimmer, no electrons will be ejected. Because whether it is in dim or in high intensity, the fact remains that the photons of that light are carrying energy less than the work function. Very interesting and very important for you to know. So when you increase the intensity of that light, which is its brightness, you don't cause electrons to be ejected. nothing will happen there, right? But then let's look at the second condition, which I said this is not much realistic in the world we live in, okay? This is a situation where you have E equals work function. Energy of a photon exactly equal to the work function. What is going to happen? Photons of light carrying energy equal to the work function of that metal will cause electrons to be ejected, but will not give them enough energy to move off the metal surface. So in this case, you would have your metal surface there. Electrons on it. And let me make this one more visible, that electron more visible. There, you would have a situation where the incident rays of your electromagnetic radiation carrying energy equals to work function will cause this electron to be ejected. So this electron dislodge, moves maybe that way or this way or up there, or even up and down back to where it was earlier. It doesn't move off the surface, just dislocated and it goes back, all right? That energy has been used to just dislocate it, to just eject it, and it goes back because the energy equals to the work function. Now, what will happen if you intensify this, if you make your light brighter? What will happen is that you will be having more of these photons of light hitting the surface of this metal. You will have more of them. But what is happening is that all of them are carrying equal amount of energy, which is equal to the work function, and therefore all they do is just to dislocate whatever electron they hit. It goes up, comes back, settles. Goes up, comes back, settles. Moves sideways, the other way, comes back and settles. Okay? Because the energy is just enough. The energy is just enough. Energy just enough to eject the electron, but not give it enough energy to move off the surface of the metal. Okay? Now let's look at the third condition, the condition I love so much. Okay? Now, the third condition, this is the condition where you've got the energy carried by the photon of light. It's bigger than the work function of a metal. Right? So that is that situation there. Right? Bigger than the metal's work function. If the incident photons carry energy that is greater than the work function, bigger than the work function of the metal, electrons will be ejected and will be provided with enough kinetic energy to move off the metal surface. Now, there is the metal surface again. We're using light that is bringing photons with greater energy than the work function. So, okay, say that is the electron there. Okay, you have the photon coming in. The energy is bigger than the work function, greater than WO. Okay, so let's say at the beginning we've got this dim light of this photons here. So the light is dim, so you've got just a few photons coming in. Okay, so 3 photons, 3 electrons will be ejected. So these 3 electrons here will be ejected because the energy of the photon is greater than the work function. So these electrons will be ejected. This photon will eject that electron. The second photon ejects the second electron. The third photon ejects the third electron. In that way, 1 electron ejected by 1 photon of light. That's what is happening. If you intensify this light, if you increase the intensity, if you make it bright, all it means is that you will have more of these incident photons of light, okay? Incident photons of light, more of them. And what does it mean for the electrons that are being ejected when you've got more of the photons of light coming in? It means that you have got more of the electrons being ejected. If 3 were ejected when you had 3 beams of this light, of these photons, now you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You will have 10 electrons ejected from that surface there. Ejected because the energy you're bringing in is greater than the work function. So what is left, the remaining energy, is converted into kinetic energy. And we know that kinetic energy is defined by half mv squared, where E is the total energy. See, E here is the total energy brought by the photon. And then WO, we know it, is the work function of the metal. And then M is the mass of a single electron, because that's the particle that is set up in motion. And V is the velocity of the electron. That's what that formula is saying to us. So that's a quick summary of the 3 conditions that may happen when we look at photoelectric effect. Right, let's look at example 2. Violet light has a wavelength of about 410 nanometers. What is the frequency of a photon of this light? So number A wants us to calculate for the frequency of the violet light. So let's look at it. A there, let's take it from the fact that we have got these being electromagnetic radiation, and I can therefore make use of this wave equation, C equals F lambda. What is the value of C? Well, C is a constant. We know it is 3 by 10 to the power 8 meters per second. This would be equal to F is what I'm looking for, times lambda, which is the wavelength, and it's given to me as 410 nanometers. But I don't work in nanometers, I must work in meters, so I must convert 410 nanometers into meters, and to do that, I must multiply by 10 to the power minus 9. Therefore, I can find now my frequency, which will be given by 3 by 10 to the power 8 divided by 410 by 10 to the power minus 9. That will be the frequency of violet light. Now, here we need our calculator to quickly help us. We have here 3 by 10 to the power 8 divided by 410 by 10 to the power minus 9. What is the answer? The answer is 7.31, and you see 7.31, and just after 1 I've got a 7, so rounding it off, it will be 7.32 by 10 to the power 14. So my answer is 7.32 by 10 to the power 14 hertz. I'm putting the unit hertz because I'm calculating for frequency. Okay, now, so that is the frequency of ultraviolet light. The next question, question B, says calculate the energy of 1 photon. Remember, for 1 photon of violet light, For one photon, that energy of one photon, E, is given by h times F. Now, what is h? Planck's constant, 6.63 by 10 to the power minus 34 times F, the frequency of ultraviolet light, which is 7.32 by 10 to the power 14 hertz. What is the answer there? Well, once again, we make use of our calculator to quickly get the solution there. It's going to be 6.63 by 10 to the power minus 34 times 7.32 by 10 to the power 14. Okay, and what is the answer? The answer is 4.85. Now look at this. Just after my second decimal place, I've got 3. 3 is far less than 5. If it's 3 and 4 and below, I'm not going to change the 5 there. The 5 is not affected when I round off. So this answer here will be 4.85 by 10 to the power minus 19 joules. 4.85 by 10 to the power minus 19 joules of energy. Okay, now let's come to the last question here, question C. Will electrons from a metal surface with work function 2.3 by 10 to the power minus 8 joules, 2.3 by 10 to the power minus 8 joules of energy, will electrons from that metal surface be ejected? And then explain your answer. Okay, now 2.3 by 10 to the power minus 8, 4.85 by 10 to the power minus 19. Which number is less than the other? This number, or the energy of the photon of violet light, it's less than that energy there. That energy as the work function of this metal that we don't know is much bigger than the energy brought by the photon or one photon of violet light. So what is going to happen there? Will electrons be ejected? No. Electrons will not, or an electron will not be ejected. You see? An electron, let me put here, an electron, because it's just one photon of violet light. An electron will not be ejected. The question further says, explain your answer. Why? Because the work function of the metal is greater than the energy of the violet photon. Okay, so because the work function is greater than the energy carried by a photon of violet light, there will be no electrons ejected. There will be no electron that will be ejected there. Right, let's have a look at example 3. Right, the wavelength of red light is 750 nanometers. And remember that we don't work in nanometers, so this will be converted into meters by multiplying by 10 to the power minus 9. Okay, that will be meters. The question is calculate the energy of a photon of red light. Okay, again, we have to calculate for the photon of red light, but we don't have frequency yet. And energy is given by HF. This then will be equal to, what is H? 6.63 by 10 to the power minus 34. But F is not what we have here. We have lambda. For us to get lambda, we will then make use of the wave equation. I'm the kind that do not want to be confused, so I work it out separately. So equals to F times lambda is 750 nanometers by 10 to the power minus 9. Remember? Therefore, our F equals 3 by 10 to the power 8 divided by 750 by 10 to the power minus 9. Let's work that out quickly. Okay, so we need our calculator. This will be 3 by 10 to the power 8 divided by 750 by 10 to the power minus 9. Okay, what is the answer? The answer is 4 by 10 to the power 14 by 10 to the power 14 hertz. Okay, so that is the frequency. Now we need this frequency to complete this. So we'll say that this will be equal to HF. Okay, let me get some space here. That will be HF, which will be H6.63 by 10 to the power minus 34 times the frequency, which is 4 by 10 to the power 14. And what is that energy? Once again, let's quickly use the calculator. 6.63 by 10 to the power minus 34 times 4 by 10 to the power 14. What is the answer? The answer is 2.65 by 10 to the power 19. 2.65 by 10 to the power minus 19 joules of energy. Okay, now that is the answer for A. Now let's move on to B quickly. Getting the answer for B. Now, B says calculate the kinetic energy of an electron that is ejected by this light. We know that from the energy equation, E will be equal to the work function plus EK. And I'm deliberately writing it this way because I've already calculated HF there, which is E. What is HF? It's 2.65 by 10 to the power minus 19 equals work function. The work function is given to us here as 1.4 by 10 to the power minus 19. So this will be equal to 1.4 by 10 to the power minus 19 plus EK. Now, what is EK? Therefore, EK equals 2.65 by 10 to the power minus 19 minus, we're taking this one to the other side, that will be minus 1.4 by 10 to the power minus 19. And what is the answer? Okay, the answer there, you can actually work it out quickly without a calculator maybe. This will be 1.25 by 10 to the power minus 19 joules of energy. Okay, so that is how you work it out. Let's quickly have a look at the last part of the question. Hope we have enough time to do that. So number C says calculate the velocity attained by the electron when red light is shown is shown on this metal, and you are given the mass of the electron there. Now let's have a look at it. Remember that EK is given by half mv squared. So this EK, which is 1.25 by 10 to the power minus 19, should be equal to half times the mass of an electron. What is the mass of an electron? 9.11 by 10 to the power minus 13. So 9.11 by 10 to to the power minus 31, not 13 actually, minus 31, okay? Then times, what will this be? V squared. In other words, we're looking for V, so we'll leave it at that point. We can do this quickly. This is going to be, you can work it out. We can say V squared is therefore equals 1.25 by 10 to the power minus 19, okay? This one must be divided by 2 if you want to, so let's just quickly do that by using our calculator. So we are going to use this function here. So we'll say 1.25 by 10 to the power minus 19 divided by 4.56 by 10 to the power minus 31. And what will that be? That gives us that. It's 523,567.39 meters per second. But then we can write this in scientific notation. It's 523,567. I can write it as 5.23, 5.24 actually, because I've got that 5 there. And then how many places did I move my decimal to bring it to 5? I've moved it 1, 2, 3, 4, 5 times. So it will be 5.24 by 10 to the power 5 meters per second. Now this electron will be moving at a very, very high speed. Now that brings us to the end of the lesson for today. I hope you enjoyed it. Go and practice more. There will be more questions on your supplementary notes. Thank you so much for watching. Bye-bye.